Good morning and welcome back. So, last class we were discussing about the Stokes system, basically Stokes linear system, and we briefly discussed its variation or formulation. The system we have considered was this one. You see, this is a system of 4 equations in 4 unknowns, 3 velocity components and 1 pressure component. And then the formulation was this one, usually the weak formulation. The weak formulation was this one, you see the weak formulation. Okay. All right. And this is a pressure free formulation. And then once you have a pressure free formulation, so you recall this one. So, you recall this space V, divergence of V equal to 0, and you have grade U grade V is equal to Fe. So, you can apply the Lax-Milgram lemma to prove the existence and uniqueness of U. So, the discussion what we have maintained last time. So, how do we get the pressure P and where is P for that? In other words, you have a 1 is the strong formulation. So, you have your 1 strong formulation here, 1 prime or 1, and then you have your 2 the weak formulation. So, what we have seen, 2 things you have to see all the time. If U is a weak solution, if U is a weak solution, this is what keep on doing, that is of if U is a strong solution, rather if U is a strong solution, that is solution of 1 implies weak solution, that means solution of 2, you see that way. Now, but weak solution gives only V, weak solution gives P, gives only U in V, you see, give that one. So, that means V is in H1, U is in H1 naught of omega q. So, we want to show that this is also a strong solution together with the pressure P. Okay. So, assume U is in H2, that is how you do it, or C2, whatever it is, you assume H2 of omega power 3. We have to show, we have to find U satisfy 1 with appropriate pressure P. So, how do you do is that? So, 2 gives, you can do an integration by parts, that immediately gives you minus Laplacian of U minus F, okay, equal, and what is your weak formulation? You just take that weak formulation for V, V as a dot product equal to 0 for all V in V. But recall that this is what you have to know, V is a divergence free vector. So, it is not the full space, you cannot conclude from here Laplacian of U equal to 0. So, what you can show is that this only implies your minus Laplacian of U minus F is in V perp. So, here is a fact which I want to, maybe you can see Temam or something, reference or some other book, Temam, some other fluid dynamics book. So, I want you to see what is V perp, this is a fact. V perp, of course, let me also keep this notation, then this is equal to H1 naught of omega cube, okay, instead of writing all the time here. So, you have your x minus x prime equal to H minus 1 of omega cube. So, you have this space. So, V perp is a subset of x prime, keep that in mind, okay, because it is in H1 naught, it will be a subspace of H minus 1. So, V perp is nothing but set of all V in x prime such that V is equal to, so the divergence free vectors, if it is orthogonal to the divergence free vectors, then your V will be some gradient of phi for some phi in L2 or H1 of omega. Okay, so you have your some phi in L2 of omega, you see. So, you can realize all your functions, Vper functions which are gradient functions. So, this will imply then, that is what you do it. So, minus Laplacian of u minus f is in Vperp, that implies that there exists p in L2 of omega such that minus Laplacian of u minus f is equal to gradient of p. To satisfy the equation, you can put a minus here, otherwise later you take minus here. Okay. So, that is how you repair the pressure, that is how you recover your pressure P. Okay. But now the first observation or a note, if UP is a solution, then that implies you can add any constant u p plus c is also a solution, for any constant c, C. So, what you will eventually get is we will discuss little more about with a pressure velocity pressure formulation. Whatever given is a velocity pressure formulation. So, your P you will be looking in L2 of omega cross P, okay, quotient out with R. So, there exists unique finally what you get is that there exists unique UP, P is the equivalence class basically in V cross L2 of omega slash the thing. So, that is what you will get it, uniqueness in this space up to f. Of course, you can fix your P by demanding integral P or something like that. So, now I want to go to the other formulation. I will not be giving all the details, but then formulation 2. Okay. Formulation 2. Okay. So, this is you can prove via Babuska-Brzee. But I want to tell you something more also. Okay. So, one fact which I will discuss a little more, dive and grade, these are the two operators coming, are in some sense adjoint operators, Okay. This I am going to see little more. Okay. So, we will go to next page and then we discuss that. So, look at this operator dive. I want to tell you few facts about it, most of them are. So, you have your this is from x equal to, once more let me write it, h1 naught of omega cube, okay, to L2 of omega. And how are you doing that? You going to divergence of u. Okay. And what is this one, and what is the kernel of V dive? Kernel of dive is nothing but your V, such that that is it, set of all V in X once more, such that your divergence of V equal to 0. I will discuss this a little later. So, your V perp is identified with, this is what we have basically used it, X B. Okay. So, phi is in V perp means equal to set of equivalent to, so let me remove that, this is equivalent to, V is in V perp equivalent to phi V equal to 0 for all V in V. So, and another fact, integral of dive, if V is in integral of dive V is equal to, by integration by parts you get V dot of nu, just because dive V is equal to dV by dxi. So, by integration by parts, where nu is the normal derivative which you are using, and but V is in X and its boundary value is 0. So, dive V is always 0. This implies actually dive is mapping from a map from X to L2 0 of omega. And what is L2 0 of omega? L2 0 of omega, where L2 of 0 of omega is equal to set of all H in L2 of omega, such that integral of H is equal to 0. Okay. So, that is what you are seeing. So, you see the dive V is always 0. So, dive V is a mapping integral of 0 to do that one. So, the final fact is that dive is a, which you need to actually prove it, I will give some hints about it. Dive is a mapping from L2 of omega, and if you have, and this you can actually prove it is to be onto. We discuss little more, that we have not solved. That means dive V equal to H for any H in L2 of omega you can solve. Once it is there, it will be 1 1 onto if you take it from V perp. You see, if you take from V perp to, yeah, that is X quotient out by V. So, that is what you will do that one, to L2 0 of omega. Okay. You have that one, is an onto isomorphism. Okay. So, I will discuss about ontoness little more later, soon, maybe in this lecture itself we will do that. Okay. So, with that let us go to your weak formulation immediately. So, what do you want to do? So, to see this ontoness, to this, let F is in L2 naught, okay, L2 naught, and what you do is that you solve this function, solve Laplacian of phi equal to F and phi equal to 0. This is in omega, this you can have, this is equal to 0 on d omega. Okay. And this will give you phi is in H1 naught, that you will get H1, you get phi is in H1 naught omega, you will get, and you take, so let me separate it, take your V1 equal to grade phi. Okay. So, then look at it, Laplacian of phi is equal to divergence of grade phi. So that implies your divergence of, so you can always solve for V1 equal to, you have that one. So you start some regularity, by regularity, so you can also give the regularity results we have not proved yet. We are going to prove the regularity. So it will give you the regularity, that you have to see this regularity. We are going to discuss in the next class about regularity. We can actually prove that phi is in H2 of omega. So that means this basically tells you that phi is in H2 of omega intersection H1 naught of omega. This is already you have. So you have your divergence of V1 equal to F, you get this one, and with V1 equal to grade phi equal in, this is not necessary, V1 does not satisfy the 0 condition. So it will be H1 of omega cube, that is all you can say. Okay. So therefore V1 need not be in V perp. So what do you do here? Now we use this condition, use integral of f equal to 0, that you assumed. So far we have not assumed. What we have done is starting with f in L2, you have this equation, that is all. But it does not have that from V perp, you have to prove that one. Okay. So integral over V1 over nu now, okay, over boundary of omega, but V1 is grade phi, that is nothing but d phi by d nu over boundary. By integration by parts, this is equal to Laplacian of phi over omega, that is equal to integral of f. Therefore that is equal to 0. So it is a V1 dot nu is equal to 0, and this condition can be used. This I will not, this can be used to consider an equation. So basically from V1 we want to remove some divergence free vector, so that it will be in V perp. So solve this solvability, I am not guessing, I will discuss little more generally, but so you solve divergence of V1 equal to divergence of W1 equal to 0 in omega. So I am removing a divergence free vector to get what it is with W. So at the same time replace keeping the boundary values same, okay, on omega, and I want to solve this W1 is in H1 of omega power a, that you can. So you need to solve this equation with this condition. As I said, I will discuss. Now you take V tilde is equal to V1 minus W1, because you are only adding the divergence free vector, and you get the divergence of V tilde is, and divergence of V equal to 0. So you get divergence of V tilde equal to f, and you get V tilde is in H1 naught of omega. So you can make that 0 boundary condition by subtracting, because V1 you can always add a divergence free vector, so that you get this equation without changing cube, okay, and that way you can view your from divergence free vectors to L2 naught is an onto isomorphism. So it is a brief discussion about it. So I will discuss little more before completing this lecture. So I will not, I do not want to take this lecture to the next stage. So what is your, I will just write Babuska-Brissy formulation, Babuska-Brissy, you check everything. I will only give you Babuska-Brissy formulation, because I need to discuss a little more in this. So, you find find u in x, let me recall h1 naught omega cube, and p in L2 naught. There you get uniqueness because you are putting a condition, integral of p equal to 0. So, that way you are fixing the constant, and your AUV plus BVP equal to FE for all V in X, and the other equation is BU phi, these are your spaces X and L2 equal to 0 for all phi in L2 naught. So, this is in that formulation. So, the exercise is you verify. So, there is an in operator form, you can write this in operator form, AU plus B star of P equal to F, and F BU is equal to 0. Okay. So, you can verify the conditions, namely the Babuska-Brazé condition and the ellipticity on the kernel of B. Okay. Conditions. Okay. And you can also get estimates, maybe you have to work little more, and you also have the estimate norm u in x h1 naught of omega cube plus norm p in L2 naught of omega is less than or equal to constant into norm of f in h minus 1 or L2, wherever you are using it. Okay. As a last discussion, a few more things. Most of these things are not really complete. You can refer books, various books on fluid dynamics and other things. So, let me do little more about that, just a little more in the next few minutes about the solvability. So, you can actually remark, you can consider minus Laplace n of u plus grade p equal to f in omega f, and divergence of u is not divergence equal to g in omega, and u equal to 0 g equal to h on d omega. Okay. So, earlier if you have recall the non-homogeneous conditions on the boundary, what do you do? That you solve that part first. That means Laplace in u equal to f and u equal to g. By trace theorem, first you find a u tilde such that u tilde restricted to g is equal to u tilde restricted to. So, let me write here, this is the same thing you are doing. So, suppose you want to solve this, minus Laplace n of u equal to f and u equal to g on d omega. By trace, find u tilde, that is g on d omega, and then you split your right u is equal to w plus u tilde, and then you know that w is in h1 naught. That is how you look for it, because the boundary condition is always like that. Okay. So, that is what you really want to do it. So, you want to basically solve this equation. So, wish to solve as I said, I am not going to discuss a lot here. Divergence of u, some remarks basically, these are all remarks. So, you have to work it out, because the details I do not have time to hear, and trying to really visualize how you see what do you say, div and grade are adjoint operators. So divergence of V equal to G and in omega and V equal to, first you solve this one, H on d omega. So what you need is a compatibility condition. So I will discuss maybe the compatibility condition later. Yeah, so there is a compatibility condition, that you compatibility condition, you need this, because integral over G over omega is same as integral of H dot of nu over d sigma over the boundary. So you need this compatibility condition to solve that. Once you solve this non-homogeneous problem, you can convert your problem into a homogeneous boundary condition problem with the divergence V vectors, exactly what we have discussed now. Okay. So these are the two things what you will be seeing each time, right? On one hand, divergence of this, what I have done here, H1 naught of omega cube to L2 of omega, in fact L2 of omega or L2 naught. So you will get 1 1 on 2. Okay. And so that's what we have seen it, V perp, that this we have seen, divergence of C. And you can also see that your divergence of phi is L2 is less than or equal to some constant into norm of phi square, divergence of phi square is equal to, oh you don't want to write the square here, okay, that is what you have seen it to x. This will be your x. Okay, that is on one hand. But what is gradient? Your minus gradient is a mapping from L2 of omega to x prime, that is h minus 1 of omega cube. This is what your minus gradient. How it is defined? So minus gradient of V should act on h1 naught. So the minus gradient of V should be h minus 1 cube. So this is in x prime, this is in x, and this is nothing but integral over psi, gradient of psi. Let me not use the V here. So let me use some other, by definition divergence of psi. So the di into divergence. This is the definition basically. You can treat it as a definition of that one. And you can see that you can compute the modulus, and you can eventually get, you just take the modulus, estimate psi and phi, and then that will give you your minus gradient of psi in x prime is less than or equal to some constant into norm of divergence of phi L2, that is less than or equal to constant norm phi into norm phi in x. Yeah, that is what you want to do it. So this is what basically tells you divergence and grade are bounded linear, okay, and you also have divergence of phi equal to 0. These are all we have proved now. So you have. So one more comment in that one, and you, so what is your range of last point? So you have your range of minus gradient is nothing but minus gradient of L2 naught in this one of omega. and that is nothing but your kernel of div of V, its perp, that you know all this one. Where kernel of div of you know that one. So what is the final theorem which requires a last proof? So the final theorem with that one I will stop. So if G is in L2 of omega, so you have to fix the lot of gaps there. Okay. So these are some of the ideas when you are dealing with certain equation. This is not that directly all the time you get from Lax-Milgram lemma. Okay, you may have to do, you have to do extra work. H is in H half satisfies integral over G is over omega equal to integral over d omega H dot of nu, then there exists unique V in X such you can satisfying your divergence of V equal to G in omega and V equal to H on d omega and the estimate. Now V, this is in X, even though it is a first order operator, what you are getting is in a second order operators only you are generally immediately derive, but here looking for this H1 space, H1 naught space. Okay. V in X satisfying constant into norm G. Oh, this is in, let me, sorry, it will not satisfy B equal to 0. This will be, my notes I done something else, H1 of omega q. Okay. And in L2 plus norm of H norm of H in H half. Okay. So with this I will stop this lecture and will now we will in another lecture we will quickly recall, not everything, some regularity results in the next lecture. Thank you. Thank you.